So at the end of the last video, we came across this important question, which was how are we going to find the tangent line on the graph of a curve where I would not be able to easily say solve for y and figure out a formula for a portion of this curve that would be a function and goes through my point of interest. This is a very complicated and unfortunate situation that we find ourselves in. But it brings us to exactly the point of this section. The idea now of implicit differentiation comes into full view. We need a way to be able to determine the derivative for different portions or on different spots on this curve, even though we're not starting with a function and we may not be able to get to a function. So how do we do this? Well, if you take a look down here at the definition, this is the idea of implicit differentiation. It says implicit differentiation is a method for computing the derivative of an implicit equation with respect to the variable x. So x is going to be treated like the variable. But every other variable that's in there, like any y's or z's or q's or any other variable in there, is going to be treated as an unspecified function of x. That is, we're going to imagine, like in an equation like this, that x is the variable and y is, I don't know, y is eventually going to have some equation, like maybe there's some formula over here where eventually I might be able to find what y equals in terms of x, but I'm just going to pretend that that can be found, even though I don't know exactly what that formula is. Now, in the previous examples, we were always able to find a value that y, or an equation that said y was equal to something specific. We did it here in example 3. We were able to do it here in example number 2 as well. But in the concept of implicit differentiation, we are just going to kind of treat all other variables as unspecified functions of x, like y is going to be equal to mystery function. We're not quite sure yet what it is. Now, this is a rather complicated sort of idea, and unfortunately we can't really do justice to exactly why this works or why we're able to make some of these statements. In fact, I have this really long note here that I'll take some time to go through. In the book, there is the following statement made about implicit differentiation. It says, the technique of implicit differentiation allows us to find the derivative of an implicitly defined function without ever solving for the function explicitly. So without ever getting again into that y equals form, I can get to a derivative. But what that leaves us with is a couple different questions. Like, what does it mean for y to implicitly be a function of x? Like, what does that mean? We've always had y equals something with x, and we know that that's a function. We said that that's an explicit equation. But if I have something like this equation up here, I don't have y equals x. And so I don't have y as a function of x. So how can I just treat y as a function of x? And also, when does this method of implicit differentiation fail? Like, does it work all the time? Does it ever not work? Well, unfortunately, the answers to these questions, as I state below, are actually well beyond the scope of Calculus 1. They're not questions that we can answer within a Calculus 1 class, even though they can be posed. So these answers are actually hinted at in Calculus 2 and Calculus 3. However, what you would really need is something called the implicit function theorem, which isn't proven until a very advanced math class called advanced real analysis you'd have to take in like grad school. And that would allow you to provide satisfying answers to these questions. So in Calculus 1, we're going to be kind of left with the very unsatisfying position of having to just pretend that, well, I guess every question that I'm going to come across that is an implicit equation could be tackled with this method of implicit differentiation because Kyle wouldn't give me any problem that wouldn't work. But we do need to note here that we're going out on a huge limb here. But the reason that we spent so much time developing all of the previous content in the previous videos for this section is to at least help make this concept a little bit easier to digest. We've already seen that it's possible to take a look at curves and see that within them there are little pieces that could be considered as hidden functions. And so what we're going to try to imagine is that y, when we take our derivative that we will do in a moment here in example 4, is going to be kind of one of these pieces that has some formula just yet to be determined. We recognize that that seems possible, and so we'll tend to just build off of that idea. So let's take a look here at example 4 and get a sense of how we actually use this process of implicit differentiation to find the derivative of y with respect to x. All right, so here's how we're going to start. We're going to start here by taking the derivative of both sides of our equation with respect to x. So I'll state that here. We will take the derivative of both sides of our equation with respect to x. So that means I'm going to start by writing out this. I'm going to take the derivative of the entire left side, and I'm going to take the derivative of the entire right side. Okay, so this is like step 1. Now, to figure out what to do with this, I should note right away that the right side is really easy, right? Derivative of 25, boom, that's 0. But the other side is a little bit more complicated here, because again, I have to recognize that I'm taking the derivative where I'm considering x as a variable, but I'm imagining right now that this y right here actually corresponds to some function formula up here that is just yet to be determined. Okay, so let's think about how we would do this. All right, so first I can notice that I have two things being added here. I have x squared and then added on a mystery function with a whole bunch of x's in it also being squared. So maybe this is sine of x squared, maybe this is x squared plus 2 all squared. This could be any formula all squared. So I notice that since these are added, I can use my sum rule to take the derivative. So I'll start with the derivative of x squared. That's just 2x. Now I have to start by taking the derivative here of mystery formula all squared. So for the sake of argument, just consider for the moment that maybe this was something like, let's say, a natural log or something like that, all being squared. Well, if I was trying to take the derivative of something like the natural log all being squared, if this is what I was trying to take the derivative of, I would note that I would need to use the chain rule, right? Because I have a complicated function being raised to a power. So I'd have to start by bringing the 2 down to the front, lowering the power by 1, leaving the inside alone, and then I would follow up with a chain rule. So I'm going to do the same thing here. I'm going to bring the 2 down to the front, leave the original complicated mystery formula alone, lower the power by 1. And then I'm going to multiply by the derivative of this formula. But you might go, wait a minute, Kyle, if I don't know what the formula is, how do I take its derivative? And you're absolutely right to ask that question. There is no way to take that derivative, but we can display that derivative. I could just write that derivative as y prime. Although you'll see that I'm not going to write it as y prime, and you might be able to see why I don't actually like to write this as y prime. Can you tell why I might not like it? Look at what I'm pointing to here. This over here is y to the first power, but this over here is y prime, like a derivative. If I use this notation, there's a really good chance I'm going to screw something up throughout the problem. I'm going to maybe misinterpret this. So instead of using y with a tick mark, instead of using that prime notation, I'm going to communicate my derivative by using this big, bulky Leibniz notation. So there's like no way I can miss that this here is y to the first power, but this is the derivative of y. That is, it's the derivative of this messy formula. I just don't know what that is, so I just write the symbol for it. Well, now notice, if I have this, can I go ahead and actually find dy dx? Can I solve for dy dx? And I should be able to say, absolutely. This goes back to a skills check question. I'm just interested in getting dy dx on its own side. So I could do that by starting with moving my 2x to the other side and getting negative 2x over there. And then if I divide both sides by 2y, I can see that I can simplify this down to be equal to negative x divided by y. So I found a derivative formula for this complicated circle that looks like this. Now, notice that this derivative formula contains x's and y's, but no big deal. I can see that if I have a point then, or in order to calculate the slope of a tangent line on this circle curve, I would now need an x and a y coordinate in order to fully crunch out that slope. Now, one thing that's kind of cool here is that we're finding a derivative formula right now for this circle. And so since we already did example 2 that dealt with this question, we should be able to go back in a moment to see how everything that we're developing here is actually completely consistent with the topics we did back in example 2. Now let's go ahead and complete part B before we go back and do that kind of look back at example 2. In part B, I'm going to be asked to find the equation of the tangent line. Well, this again should be really simple to do. Again, I know what I'm looking for. I'm working with the point 3, 4, which we'll say is up here, and my tangent line looks something like this. I should be able to easily state that in order to get my slope, I would just have to go to my dy dx and evaluate it at the point 3, 4. Now to notate this, it's customary to put a big vertical bar and then say that x comma y is equal to 3 comma 4. This is some really bulky notation, but it says I'm going to go to the thing called dy dx, and in place of x and y, I'm going to plug in the values 3 and 4. Now you don't have to use that notation. If you wanted to, you could just jump right over here to plugging in x and plugging in y. So notice I get a slope of 3/4, or negative 3/4. My point, of course, is 3 comma 4, and so again now it should be really easy to go ahead and write the equation of that tangent. So that's going to be y minus 4 is equal to negative 3/4 x minus 3. And if I simplify that, I'm going to end up with negative 3/4 x. And again, I end up with something like 25/4. So notice that this is again actually the exact same equation that we ended up with back in example 2. And I want to go back and take a look at that just to confirm. If I go back to example 2, all the way back up here, notice I have the exact same formula written down. Now the other thing that's kind of interesting is notice that in example 2, we were looking at the top half of the circle, and we were able to find a function for that. And so then we were able to take that function's derivative, and we got to something that looked like this. Now notice that actually, if I was going to go ahead and think about my derivative here, I had a derivative of negative x over this square root. And in this new example, I have a derivative that was negative x over y. So really quickly here, I'm just going to go ahead and put in an important note. Note that since we were told at the beginning that y, or we could show that y was going to be equal to a positive square root of 25 minus x squared, since we're working with the top half of the circle, then it would be totally appropriate to say that dy dx, which is negative x over y, on this portion of the circle, I could replace y with 25 minus my x squared, right? So I'm just showing that my derivative could be written as negative x over y, but if I'm working on this top half of the circle, then y is the same as this, and so it could be replaced with this right here. And notice again that if I was to scroll back up to example number 2, this is completely consistent with the derivative that I had here. Notice this was the derivative negative x over, and look, it's negative x over y. The value in the implicit differentiation method that we took down here on the left side is that it allowed me to do this without ever having to solve for the value of y directly. Okay? So this is a really, really awesome technique that allows me to take, again, an implicit equation and immediately find a derivative for any point on the curve, of course, as long as it's defined. You'll note here that, of course, at the point of 0 for the value of y, I would get undefined for this derivative. And so I do have some problems there. Although that's actually not too bad, because you'll notice that when y is 0, I'm at these edges of the circle, and I do end up actually with tangent lines with undefined slopes. So everything here works out beautifully with this implicit differentiation technique and the results that I have. And we'll practice this a lot more in the examples to come.